Today we're going to look at functions of two variables and limits and see if limits exist. This is a continuation of our discussion on limits of functions in two variables. Recall, in two variables, f is a function that takes r cross r into r, defined as follows: f of ab equals c, where a, b, and c are real numbers. So let's do an example, and let's talk about whether this particular limit exists or not. And it's much easier to start with the answer in mind. So let's look at this problem. Suppose I want to look at the limit as x and y approach the origin. The origin is an easier point to consider of this quotient: x squared minus y squared over x squared plus y squared. Now, when looking at this limit, obviously we can't substitute 0 and 0 in for x and y respectively, because this would result in an undefined expression. So it becomes necessary to examine what we really mean by this. If you recall, this idea of x comma y approaching 0 comma 0 really means we're looking at some local neighborhood around the origin. In particular, the origin is the point of interest, and we're looking at the locus of all points that are a fixed distance, d, between the origin and xy. And what do they form? They form a circle. So if one thinks about what this limit means, when one talks about simply the notion of x comma y, which are an infinite set of points converging in on 0 comma 0, we realize that we're talking about it inside of the circle of radius equal to length d. There are many ways that we can converge on the origin. For example, there's a path that you can take along here. There's a path that you can take along here. These are all points. These are paths that you can take along here. All of these are points that are converging in on the origin, independent of path. So a very intuitive notion, and this is an intuitive idea, this intuitive idea is that the limit exists if the limiting value, which we denote as L, is path independent. What does that mean? It means that whether you take this route, or this route, or this route, the value that you achieve must be the same. If we can show that one route produces one value, produces a value, say L1, and another route produces a value L2, and that these L1 and L2 values are different, we can conclude that the limit does not exist. So, in our original problem, if we go back to our original problem, if we can look at this quotient and show that for a specific path, for two different paths, the quotient produces a different result, we can show that this limit doesn't exist. So let me choose one path. Choose the path y is equal to x. I think you can look at that path in R2 and realize again that we're talking about a neighborhood around the origin. And the point y equals x, or y equals x, is a line. So one is talking about the set of all points, the locus of all points that are converging in on the origin along this line, y is equal to x. If we look at a path along this line, this limit of two variables can be converted into a limit of one variable in the manner of speaking. Every place I have a y, I can replace it with an x. So the original limit was this. Now, if I replace y with an x, I'm still looking at x and y converging on the origin along the line y equals x. What does this mean? It means that this quotient, the numerator, can be replaced as x squared minus x squared, because we know that y equals x, divided by x squared plus x squared. and that equals 0 over 2x squared. Of course, here I'm taking the limit, and that, of course, is equal to 0. On the other hand, if I choose y equals 2x, I can look at the limit as x comma y approaches 0 comma 0 of x squared minus 4x squared over x squared plus 4x squared, and this is equal to the limit as xy approaches the origin of negative 3x squared over 5x squared, which equals negative 3/5, which clearly does not equal 0. Therefore, our conclusion is that the limit does not exist.